name is Jack Michael. This is Physics 2211, Lab 2. A brief overview of what we're going to be looking at. First, we'll have introduction, data observation and models, code, discussion, and finally conclusion. A preview of what I found. Gravity and drag are both forces that act on a free-falling object and influence its motion. The purpose and fundamental principles in this lab are seeing an object's motion that is dropped and falls to the ground. The fundamental principle at work here is Newton's second law. I'll represent this with both a computational model that considers only gravity and another model that considers gravity and drag. This will be compared to the actual data which was collected on a object falling to the ground. Looking at Newton's second law in depth, it states that force is equal to the change in momentum over time, as you can see in the bottom, which is derived from the top formula. It indicates that changes of momentum within the system. It indicates changes of momentum within the system and its surroundings. Now, two important terms that we need to know, as I've been saying, the forces of gravity and drag. Gravity is a force of attraction which pulls an object towards the center of a body of mass. The result of Earth's acceleration due to gravity is about 9.8 meters per second squared. That's the notation for acceleration. And drag is a resistant force that acts against a motion of object falling through air or water, some viscous fluid. It acts in the opposite direction of velocity. It's almost like a friction between the air and an object. Now, the procedure to observe this is 1. Record a video of object falling and upload it to the video into the tracker software. 2. Use the center of mass, calibration stick, and axis to properly record the fall data frame by frame. 3. Create 2 computational models, one showing only gravity's effects on the falling object, and another showing gravity and drag using the code. And 4. Compare the computational models and the tracker data in relation to Newton's second law. Now, here is my tracker data. As you can see, on the left is the y component of the position. The middle is the tracker data, each of the points frame by frame. And the right is just the table of all of my data. Now, here are the observations that I used to tweak the code model. Start time 0 seconds, end time 0.767 seconds. Initial velocity of 0 because it's initially at rest. And the initial position within the tracker was as shown. The system surroundings. The system in this case is the pillow, and the surroundings are anything else that affects the movement of the object, which was air and gravity. These observations will be used to see the impact of gravity on the object's motion. Now, here's the code that I made to represent the falling object. Again, using the values I just mentioned. I changed the position to this, the starting velocity to 0, like I said, and the end time to 0.76 or 0.767 within the glow script. Net force was set equal to weight, and weight force equation was also added. And the velocity update and position update formulas were added. Right here on the right, you can see my final code. That's, again, just for only gravity, not accounting for drag. Here's the result of the gravity model. It has a constant acceleration. And the gravity and drag model, what I changed from the gravity model, I added a b value of 0.0889, which I calculated from the difference of actual gravity as shown in the video versus the given g, which is 9.8. The drag force equation, net force equation, and arrow equation and arrow scales representing opposing drag force. Here, you can see the code. This was the result. As you can see on the left, here are the gravity and drag vectors. As you can see, the gravity vector is larger than the drag vector, meaning that the force is still net downwards. As you can see, it does not curve nearly as much. That's because the acceleration due to gravity with drag is less than without drag. Comparison. So here you can see the experimental model, the model with gravity, and the model with gravity and drag. Overall, both models were still similar to one another. However, since the gravity model did not take into account drag, the position fell went much further in the same amount of time, since the object had nothing preventing it from fully accelerating. Potential errors. Mistakes could have been made using the tracker software. Additionally, in the video model, it would be impossible to not have drag interacting with the falling object. Which model better predicts terminal velocity? The model exhibiting gravity and drag influencing the motion of the object better demonstrates terminal velocity. The graph becomes more linear towards the end, which shows that the object reaching terminal velocity, which the force of gravity and drag are equal, where the force of gravity and drag are equal, making the net force equal to 0, so it would no longer be accelerating. What if the object was thrown? Well, an object thrown is not exempt from reaching terminal velocity. Initially, if thrown downward, the object would have a faster initial acceleration, meaning a faster initial velocity downwards, so it would reach terminal velocity faster. If it was thrown horizontally, that would not change anything about its vertical movement. However, it would keep a constant velocity, unless accounting for drag in the horizontal direction. The computational model still demonstrates the velocity becoming more constant towards the end. In conclusion, Newton's second law is observed in the video model through the object's acceleration, mass, and force interaction. Force grows as mass grows, the same with acceleration. Identifying which computational model better represents the experimental model, the gravity and drag model better exemplifies what is going on in the experiment, since the real world object has to undergo the drag force in addition to the gravity. The gravity and drag computational model is near exactly like the experimental video model of buzz being dropped, and data collection was overall very consistent. Thank you.